it's driven by your questions, and I will answer for as long as I can, and we'll go from there, okay? How are you guys feeling about it? Nervous? So what you're at the point in the term of discovering is that there's a lot of material, and probably the past 2 or 3 days that's really driven it home to you. We go through a lot of stuff in this class, and that's because we're covering a complete subject of biochemistry in one term. And the subject of biochemistry is taken by majors in 3 terms. It's taken by students that are pre-med, pre-dental, pre-health in 2 terms, and it's taken by you guys in 1 term. Now, obviously, in that 1 term, you're not taking things at the same level of depth that the students in the other classes are taking, or you really would be going crazy. But nonetheless, what you're discovering is that things hit you pretty quickly. I won't tell you I'm perfect at it, but I try to make the exams be reflective of the material as a whole and not overly specific, okay? So I try to, get the big picture of things, and I will tell you, as I tell everybody, that when I write the exams, I go to my highlights, and I look through the highlights and decide what did I talk about, and then what should I be asking questions from. So the highlights are a good starting point to think about things, okay? Things do change from year to year, which is why I absolutely don't recommend using old exams, because you'll waste your time futzing with things that perhaps we haven't talked about. So it's just not a good idea to do that. The exams give you the idea of the format, and that's about it. Okay? All right, that said, I will shut up and go for any questions that you guys have. Yes?
I had a question in regards to the exchange.
Okay.
Hemoglobin.
Okay.
Actively metabolizing tissues spit out protons.
Mm-hmm.
Protons actually bind the hemoglobin to change the structure in order
Okay.
for it to release.
Okay, so what I'm going to do is with each question, I'm going to repeat it so that the people who aren't close to the microphone out in TV land will get to hear it. The question was, active respiring tissues are actively letting go of protons. Is it those protons that binds to hemoglobin and causes the structural changes that I talked about that gives rise to the release of oxygen? The answer is basically yes. Okay. There's not necessarily a one-to-one relationship between this proton came off and this proton went on over here, but the fact that there's a higher concentration of protons around actively respiring tissue means it's more likely that protons from that area are going to bind to hemoglobin. So the answer is yes, but don't get it stuck in, this one to this one to this one to this one. Okay? Yes? Sure. This would be really nice to have the projector working, but I don't have that, unfortunately. So let me tell you a little bit about turns. And turns are really the biggest variables in protein structure. It's because that turns can happen in so many different ways and so many different angles that there's so many different ways that this can happen. So I'm going to say a little bit about secondary structure first, because that's relevant to the turns that you're asking about. And then I'll talk about the turns. So secondary structure, of course, are interactions between amino acids that are close in primary sequence. And those are typically less than 10. And the alpha helix and the beta strands are the best examples of those, by far. That's probably 99% of the secondary structure of a protein. Turns happen because you get something in the sequence of a protein that isn't consistent with those other structures. So it might be something that's got a bulky R group, or it's interfering with the last amino acid that was in that secondary structure. Whatever it is, it's causing something to not go consistently with that either helix or stranded structure that you have with the beta strands. When that happens, then an irregular structure appears, and that irregular structure we can think of as a bend or a turn. And those bends or turns, we can reasonably predict where they occur. We don't reasonably predict exactly their angles. Okay? So one of the things that I tell students to think about with respect to turns is that proline is very commonly associated with turns because it's got that lack of flexibility of its backbone because the R group is coming back and connecting with that alpha amine. All right? So the other amino acids all have a single bond between the carbonyl carbon and the alpha amine. That's the peptide bond. Okay? When we have the alpha amine tied up with an R structure, an R group, all right, then there isn't the flexibility because you can't bend it because the rest of the ring holds it into place. So proline has this very relative, I shouldn't say very, but relatively rigid structure compared to the other amino acids. And it's that rigid structure that causes this deformation that I talk about with respect to turns. So where you see a proline, commonly, not absolutely as you've seen, but commonly you'll see it associated with turns. And there are other amino acids that are involved in turns. I don't mean to say that proline is the only one, but proline is a very common one that is. Okay? Yes? Yes. Yeah. So glycine, the question is, glycine is very flexible, I said, so why do we see glycine associated with turns? And I guess my best answer to that, and I'm not a protein chemist, but my best answer to that is because it can be. Because it's possible for glycine to enable turns to be there. Okay? Glycine itself doesn't cause a turn. Glycine would be quite happy to go with any of the other structures. But where it's adjacent to an amino acid that isn't fitting, it facilitates that amino acid from jumping out of the structure it's in and making a turn. That's the best answer I can give you. Yes? So the question is, does proline automatically cause a turn or just often? Often. Yeah. So proline, you've seen, for example, that proline is found in the helix of collagens. I had a very good question from a student by email who asked me the following question. And the question was, okay, so collagen is a series of helices, 3 different helices that are interwound with each other. How come that isn't tertiary or quaternary structure? And I said, well, technically it could be quaternary structure because when you have things that aren't close to each other in primary sequence interacting, different strands interacting, you're talking about really quaternary structure. Okay? But what this is a semantic issue. So people talk about collagen being a fibrous protein more because it's fibrous in nature. It just goes on and on and on and on and on. But the reality is that there are strands that are interacting with each other. So don't get too hung up on the semantics of that. Okay? But that's what's up. And that's why proline is not always associated with a turn. We see it, especially in collagen, in a helix. Proteins, I will tell you, proteins will confuse you. So don't get too hung up on the sequences because you can take something. There's no one rule that says this is going to be a turn, this is going to be an alpha helix, or this is going to be a beta strand. It depends on the context and the environment in which that amino acid is actually found. And so something that might be in a turn in one protein will be part of a helix in another protein, et cetera, et cetera. And it's one of the reasons why I told you that Leventhal's paradox says that it's, a million times greater than the lifetime of the universe to solve that problem, because there's a lot of variability that's there. We have some general rules, and I've given you those sort of general rules, but that's why I haven't asked you to memorize really any rules other than, say, proline being associated with bends. I mean, but even that, as you've seen, is not an absolute. Okay? Yes? Can I go on about counting charges on a polypeptide? Okay, why don't I do that on the board? How about that? I hope this shows up on the camera, okay? The lighting in here is not good. That's as bright as it gets. Okay, let's imagine I've got a polypeptide. Find a piece of chalk. Here we go. let's just say I've got a polypeptide that has, I'll just make up a sequence. It has glycine. It has arginine. It has aspartic acid. And I'm using the abbreviations here. I'll give you the full names if I put it on an exam. And it has methionine. Okay? And I told you that, let's say, and again, I would give you these on an exam, but let's say I told you that the alpha carboxyl, the pKa, is 2.2. The alpha amine is 9.0. The R group carboxyl is equal to 4.4. And the R group amine is equal to, let's say, 12. Okay? So let's say I gave you that on an exam. And I said I've got this polypeptide, and the polypeptide is in a solution at a pH of, let's say, 5.5. Okay? And then I would say, what's the charge on that polypeptide? Okay, everybody understand the problem? So, how do I solve a problem like this? Well, first of all, I have to know all of the different groups that can ionize. And you need to know which groups can ionize. That's why I told you you need to know the ones that have the amines that can gain and lose protons, the ones that is the R groups that can gain and lose protons. That includes the amines and the carboxyls. In the amines, it's histidine, arginine, and lysine. In the carboxyls, it's aspartic acid and glutamic acid. So some of the things that can ionize are R groups. The other things that can ionize are the alpha carboxyls and the alpha amines. Well, every polypeptide has an alpha amine and it has an alpha carboxyl. We'll decide whether those protons are on or off later. Okay? So I have to remember that I've got an alpha amine, for which I've got a pKa. I've got an alpha carboxyl, for which I've got a pKa. And then I have to decide which of these guys have R groups that can gain or lose protons. Well, arginine has an R group that is an amine. Aspartic acid has an R group that has a carboxyl. Glycine does not. Methionine does not. So now I've identified all of the different parts that can gain or lose protons. The next thing I do is I apply the rule that I gave you, and you need to know the rule, and this is the place where students trip up. They forget the rule because they remember it as above or below. Okay? It's not a good way to remember a rule. Remember the rule the way I told you. The pH is more than 1 unit below the pKa. Proton is on. The pH is more than 1 unit above, or 1 or more units above the pKa. The proton is off. Right? So we apply the rule. pH of 5.5, 5.5, if we think about the alpha amine, is below the pKa of the alpha amine by more than 1 unit. So that proton is on. When an amine has a proton on, it has an NH3 and a plus sign. This is an R group amine. An R group amine has a, in this scenario, has a pKa of 12. pH of 5.5 is more than 1 unit below the pKa of the R group, so that proton is also on. And I have another plus. The next one is the R group carboxyl. The R group carboxyl has a pKa of 4.4. The pH is more than 1 unit above that. That means that the proton of the R group carboxyl is off. It has a charge of 0. A charge of -1. My mind is not working. I did have a beer before I came tonight. Does that count for anything? Okay. All right. And the last is the alpha carboxyl. Okay. The alpha carboxyl has a pKa of 2.2, pH of 5.5. pH is more than 1 unit above the pKa, So the proton is off. And I simply now add up the charges. Got a minus, a plus, and the charge is 0. Make sense? Questions? Yes, ma'am. Yeah. Yeah, it's a good question. It's by convention that when we write a sequence of a protein, that we write the amine on the left and the carboxyl on the right, but it's just a convention. As long as you kept track of both of them, you'd be all right. Yeah. Yeah. If the amine lost its proton, any amine that loses its proton has a charge of 0. Right. Okay, because remember that what's happening when we gain or lose a proton has a charge of 1. So when we lose a proton, it's always going to lose 1 charge. If it starts out as a +1, it loses 1 charge, it's going to have a charge of 0. Right? And the carboxyl started out at 0. If it loses a proton, it's going to have a charge of -1. Okay? Clear as mud? Nobody's smiling. You're smiling. Does that mean you're the only one here that's getting it? Okay. Others are smiling now. That's good. Yes? The only ones that we worry about in that sense are those 5 that I listed. It turns out there's a couple more that are, but to keep things simple, I'm not making you know them. Okay? Sure. The R group amine ones are the histidine, lysine, and arginine. And the R group carboxyl ones are the aspartic acid and the glutamic acid. Oh, yes, I'm sorry. I am if you are. Yeah. Sure, sure. So let me back up a little bit and give you the build up to KCAT. Okay. So we talked about enzymes and we talked about velocities. So if I said to you, what's the velocity of an enzymatic reaction? How many of you feel that you could tell me what that was? It's not a pop quiz. I'm just curious if I communicated that or didn't communicate that. Nobody's got that? Okay, what is it? So the velocity of a reaction is the concentration of product per time. That's what the velocity is. How fast you're making something, if you think about it. The velocity of a car is how fast the car is moving. The velocity of a reaction is how fast you're making something. What you're making is the product, and so it's the concentration of product divided by time. Okay? I use the analogy in class of the product being the output of a factory. So a factory puts out things, and a factory has a capacity. Okay? Doesn't matter how many raw materials you put into it. At some point, if you saturate the factory and you only have a fixed number of workers and an assembly line that only moves so fast, there's only X number of cars or widgets or whatever it is that you're making that can be made per given day, per time. Okay? If I double the number of factories, then I can double the number of cars or whatever it is that's being made per day. Right? So I use that analogy to point out that when we talk about an enzymatic reaction, that the velocity depends on how much enzyme that we use. If I double the amount of enzyme, I will double the velocity. Well, the maximum velocity for a reaction is equal to the velocity that you get when the enzyme is saturated with substrate. It's the equivalent of the factory being saturated with parts. There's no limit for parts. There's no limit for workers. There's only a limit in how fast the conveyor belt is putting things out. Right? That's what's happening with an enzyme at Vmax. There's no limit of substrate. There's no limit of the enzyme making product. The only limit is how many enzymes you've got. So if you make more if you put more enzymes in there, you will get more product. And if you get more product per time, you've increased the velocity. So I say that because it means that the velocity is not a constant for an enzyme. Vmax is not a constant. Vmax depends on the amount of enzyme that I use. And that turns out not to be very useful for us. It's not very useful. So we want something that's independent of the amount of enzyme that we use. So Vmax is equal to concentration of product, those brackets mean concentration, over time. Okay? Well, this depends on how much enzyme I've got. What if I said, let's take the enzyme out of the equation? What if I did this? I said product divided by concentration of enzyme what happens is the concentrations cancel out. So I started with a concentration, but I've got a concentration divided by a concentration, and the concentrations actually cancel out. So what I end up with is the units on something that corresponds to what's called per time. I haven't told you that, but that's what it is. In reality, what you get is a number, 150 per second. That's what it means to say per time. And what this means, getting back to your question, what this means is 150 molecules of product per molecule of enzyme per second. Every enzyme in this case is making 150 molecules of product per second. Okay? That is a number I can compare one enzyme to another because it doesn't depend on the amount of enzyme because it's telling me the actual amount per enzyme. And because of that, kcat is a very good number to compare enzymes for as far as velocity goes. Yes? 150 molecules of product per enzyme per second. What's that? Yeah. 150 molecules of product per molecule of enzyme per time. It would be the equivalent of 150 cars per factory per day. General Motors, right? So if I had 10 factories putting out 3,000 cars per day, then I said 3,000 cars divided by 10 factories, I'm getting 300 cars per factory per day. Make sense? Yes? Okay. Anything else on this before we move on?
So since you're on Vmax, what about for the KM? We have
Okay.
half of Vmax over 2. You said you want more.
Okay. So KM is not half of Vmax over 2. That's an important point. It's not that. So KM is equal to the substrate concentration that gives Vmax over 2. Okay? So I determine what Vmax is. There's my Vmax. Once I know Vmax, I can say, oh, well, if that's Vmax, then half of it's going to be right there. I say there is the velocity that corresponds to half Vmax, and there is the substrate concentration that corresponds to that velocity, and the substrate concentration that gives Vmax over 2 is equal to the Km. Now that could be just something that you memorize, but Km is actually a quantity that we use to measure the affinity an enzyme has for its substrate. The higher the Km, it means it takes more substrate to get to half Vmax. That enzyme doesn't like its substrate. If it takes a lot of substrate to get to half Vmax, the enzyme is twiddling its thumbs, not paying any attention to the substrate. On the other hand, if the Km is low, the enzyme is grabbing the substrate as soon as it sees it. It's got high affinity for it, and it gets to half Vmax very readily. Does that answer your question? Now, you had a question. Any more on this? Okay, go ahead.
I was having a hard time understanding number 4, and I was wondering if you could work it out with me.
Okay, so number 4 says calculate the pH of a solution obtained by adding 1 milliliter of 0.1 molar HCl to 99 milliliters of buffer solution containing 0.0063 moles NaH2PO4 and 0.0100 moles Na2HPO4. You like that one? Okay. So that one builds on, this is problem number 4 of Henderson-Hasselbalch problems, and it builds on the first 3 that I asked in this set. Okay? Now, I'm going to answer number 4, but if you really want to understand this, you really need to go through and do 1 through 3. Okay? Because what 1 through 3, I'm sorry, it's more like 2 and 3. What 2 and 3 tell you, they point out to you, is that what a buffer does. What a buffer does is remarkable. If you take the same amount of acid, you add it to water, you will see that in this example that I gave, the pH of water changes by 4 pH units. And you take the same amount of that acid and you add it to the buffer I put in this problem, and what you will discover is the pH changes by about 0.03 units. The buffer really does resist that change. There's a hummingbird right there. That's cool. He wants to learn some biochemistry. Okay. That is cool. Where's my food, man? Okay. So let me just step you through this problem. Okay. What's that? I didn't hear what you said.
I have number 3 too.
Okay, that's fine. But I'm just telling people what that is. Okay. So that's what this problem is here for. It's not just to throw a bunch of numbers at you, but to demonstrate what a buffer is doing. Okay. So since you've asked, I'll go ahead and just go through this real briefly. Well, I never tell what I'm going to ask on a test. So I can tell you with 100% assurance that I will ask you some question on the test.
Like that?
I didn't say that. How's that? Okay. So you've got 0.1 milliliters of HCl of 0.1 molar. And you got 99 milliliters of buffer. And it's got 0.0063 moles of NaH2PO4 and 0.01 moles of NaHPO4. Okay. And I say, what's the pH of this solution? Well, first of all, we need to know that this is a phosphate buffer, and I forget what the pKa was. Let's see, it's up here. pKa is 7.2. Okay? Now, I'm going to step you through the sort of strategy of this thing. Okay? The strategy is when you understand the strategy, this is why I think the practical component of mathematics and the practical component of chemistry makes so much more sense than getting lost in a maze of numbers. Okay? Now, I'm not saying that you shouldn't be able to do numbers, because you should be able to do numbers, right? But you shouldn't let numbers throw you for a loop. You should look at the practical side of things. All right? Well, let's think about this. We've got a solution. Let's look at this from the top down. All right? We have a solution that's got some acid and it's got some salt. How do I know that? Well, the acid always has more protons than the salt. It's an NaH2. This is an Na2. It's actually Na2H, right? So we have more protons on this guy up here. We know the pKa of this guy, of these guys, correspond to 7.2. And what am I asking you? I'm saying, what is the pH of the solution? Well, we know from Henderson-Hasselbalch that pH equals the pKa plus the log of salt over acid. Right? Everybody with me? I'm giving you that on an exam, right? You don't need to know that. pH equals pKa plus the log of salt. Well, you know the 7.2. You know that this is what I'm asking you for. So somehow you're going to have to divine the numbers for this. Right? Now notice I'm thinking through this problem. I'm not putting anything in a calculator. I'm not doing anything but thinking through the problem. Because once I think through the problem, then the calculator becomes the trivial part. Okay? Well, how much salt do I have in this solution? I have that much salt. Right? All right. So, plus the log of 0.01 moles of salt. How much acid do I have in this solution? Right here, right? 0.0063 moles of acid. Is that my answer? Why is it not? I'm forgetting something, right? What am I forgetting? HCl. HCl, this is what I started with, right? You should be going through the argument I'm giving you right here verbally. You should be going through this argument in your head when you're doing a problem before you put anything into a goddamn calculator. Okay? This is why you should think through problems. All right. So now if I know the number of moles of protons that I'm adding, what's going to happen to the amount of salt and acid? What's that? They're going to change. How are they going to change? Let's say that I had Z moles of HCl that I added. What's going to happen to the amount of acid? I'm going to gain Z moles, right? What's going to happen to the salt? I'm going to lose Z moles, right? So now I say, well, this is going to be minus Z, and this is going to be plus Z, right? I have one thing I have to know. How many moles of protons do I have? Right? Does that look complicated? It's not. Okay? The numbers, if you jump at the numbers are just going to throw you for a loop. Well, what's Z? Well, Z is volume times concentration. What's the volume? 0.1 mils, which corresponds to, it was a 0.1 or was it 1 mil? I thought it was 1 mil, isn't it? Did I write down 0.1 mils? It is 1 mil. Okay, yeah, I thought it was 1. Okay. It's not 0.1. It's 1 mil. 1 mil is how many liters? 0.001 liters. What's the concentration? 0.1 moles per liter. Sorry. 0.1 moles per liter. Do you see anything canceling out there? I do. Liters cancel liters. And my Z is equal to 0.001 times 0.1. You can punch that in a calculator if you want, or you can simply write it down here and say minus 0.001 times 0.1, 0.001 times 0.1. That would be the answer to the problem. Now, is that simpler than the way you typically work a problem? I hope it is. Because you learn the steps in the process and not some mindless thing about numbers. Questions about that? I won't bite you, I promise, if you ask a question. You have a puzzled look on your face. I have those thoughts. I have those days. I have weeks like that sometimes.
So the top equation, I'm just forgetting all of the times the 1 milliliter by you said something and I missed it.
Well, concentration is always equal to moles per liter. Right? So here's a mistake that I don't know why chemistry hasn't hammered this into every kid's head. But I will tell you that, and I'm not blaming you, I'm blaming chemistry, okay? I will tell you that 3/4 of the students that come to my office and I work this problem with them, they will do the following. I'll say, well, concentration right here, right? 0.1 molar. And so what will they do? And I'll say, well, that's 0.1 moles per liter. And they'll all do this. Capital M stands for moles per liter. It's not the same as moles. So if you think capital M is moles, you're going to be in trouble. It'd be like saying 40 miles per hour is 40 miles. It's not. Moles per liter and moles are completely different things. So this is moles per liter because this was moles per liter. Okay? Well, if I know this is moles per liter and I've got liters, I can figure out moles pretty quickly because I know the liters are going to cancel if I multiply them. Right? So now I've got this number of moles. And another thing I recommend that you do, especially if you're thinking about about partial credit on an exam, label, 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 label. The more we can figure out where you went wrong, the more we're able to give you points. But if all we see are numbers that are unlabeled, I hate to tell you, but you're going to have a 0. Okay? So if you label things where we can see what you've done, we say, oh, there's where they made their mistake. I know how far they got in the problem before they had an issue. Make sense? Okay. Yes?
So just kind of getting a basic concept. You talked about this test primarily like math, almost mathematical equations, but really the only thing.
There are some. I don't mean to say this is all math. It's not all math. Okay? So please don't take that as meaning it's all math. We've talked about plenty of things that have nothing to do with math. So math is a part of this. And math is a bigger part of this exam than it is of the other exams. But it's not all about math, no. Does it make you feel better or worse? Okay. Wait. Anyway, I'm sorry. So your question then?
I was just wondering, like, with the
Lineweaver-Burke,
yeah, what exactly with those equations on there, like what were we supposed to know besides that you used
Sure.
reciprocal?
Sure. Okay. So that's a good question. It's a very common question. Okay. So in fact, I had a student in my office today from the eCampus, and her question was, so why Lineweaver-Burke? Why do I care about Lineweaver-Burke? How do I get Lineweaver-Burke? Right? I mean, I can tell you, well, you take the double reciprocal, you take the reciprocal of everything, and you get it. All right? But that doesn't really have a lot of meaning for you. Right? So if you'd like, I'll spend a few minutes talking about why Lineweaver-Burke and why it's powerful and how you do it. Is that kind of your question? Okay. Okay. Lineweaver-Burke is simply a tool to learn something. Okay? It's nothing more than that. It's just simply a tool to learn something. Her first question to me was this. I had this drawn on a piece of paper, and she looked at it, and she's a very good student, and she scrunched up her face, And she said to me, how in the hell do you get that? That's just a really good question, okay? Most people are afraid, to ask questions or whatever. And she asked me this very good question. Well, how did you get that? Okay? And I said, okay, it's a good question. I don't get it like this. That's not the way I get it. The way I get it, I start with a blank plot, and I do an experiment. And the experiment I do is that 20 tubes that I talked about. So I got 20 tubes, 20 test tubes. I'm only going to have 10 here, okay? I got 10 test tubes. I'm lazy. All right? I'm going to do 10 different reactions, and I want to study the relationship between the amount of substrate that I have and the velocity of a reaction. That's really what I'm trying to study. Okay? So if I do the experiment, I want to have as many things the same as I can, and I only want to have one thing varying, and then I want to see the effect of that one thing varying on my experiment. So each tube gets the same ends, gets the same enzyme, and it gets the same amount of enzyme. Each tube gets the same buffer and the same amount of buffer. Okay? Each tube gets substrate, but that's where the variable comes in. Every tube gets a different amount of substrate. That's the one thing that's changing in the experiment. Okay? So I can ask the question, so when I mix these together, and I do that thing like I did today where I watch how much yellow color appears. The yellow color is telling me how much of a reaction is going on. That's a velocity. How much, the more yellow color, the more velocity, for example. I can measure the velocity of a reaction by whatever means I use. I measure the velocity of a reaction, and I get 20 velocities. Velocity 1, velocity 2, velocity 3, velocity 4. Okay? These velocities are not all going to be the same. Why? Because these velocities are going to depend on how much substrate I put in each one, the one variable that I had. Everybody with me? Let's say I measure a velocity here that says I got 2 millimolar per second, and the numbers don't really matter here. And the substrate concentration I used was 10 millimolar. I would go up here with my velocity to a place of 2. I would go down here to my substrate concentration of 10, and I would say, there is my first point. Right? And then I would do that for the second tube, the third tube, the fourth tube. Each one would have a different substrate concentration, and each one would appear somewhere on a plot, and I would make those points. And that's what I would see. Okay? So the line that I draw to show you these things is simply connecting the dots. That's where the line came from. Everybody with me? Now, what is line? You asked me about Lineweaver-Burke, and I'm giving you velocity versus substrate concentration. Are you ever going to get to Lineweaver-Burke, Ahern? Okay. Here's what's going to here's Lineweaver-Burke, right? Well, why do I care about Lineweaver-Burke? I care about Lineweaver-Burke because I look at this and say, where does that flatten out? Where is that maximum velocity? Is it there? Is it there? Is it there? Where does it flatten out? I have to make a judgment in looking at that plot and telling where it flattens out. We don't want science to be as, where do we want it to flatten out? We want it to be objective. We want to be able to have something that's going to tell us here is what that value is. Because this value is going to be Vmax. And if this value has some fluctuation, then Vmax over 2 has some variability, right? And that means, therefore, that Km can have some variability, right? So I want to have an objective measure. That's why I do Lineweaver-Burke. So I can take the same data that I had here and plot it on a Lineweaver-Burke. And this is what, I loved her expression on this today. She said, it changes from this into a straight line? And I said, yup. She said, how? And I said, well, there's a mathematical reason why a hyperbola becomes a straight line, but I don't think you want me to tell it to you. Okay? But there is a mathematical basis. That's why these plots were done. But the bottom line is a hyperbola, which is what this is, converts into a straight line if we have 1 over v, if we take reciprocals of everything. So when I say take a reciprocal of everything, what does that mean? Well, here's 2. Reciprocal of 2 is 1/2. Here's 10. A reciprocal of 10 is 1/10. I would take those numbers, I would plot them on here, and that's where the straight line comes from. Now you'll notice I only drew half of the straight line. She said, how come they draw a dotted line down there? Anybody know why you draw a dotted line down there? And by the way, you don't have to draw a dotted line, but why books do that? Because what? You're going negative. You can't have a negative substrate, so this is just an extrapolation. It's just a theoretical. We're just drawing the line down to the axis because drawing it down to the axis gives us an important parameter. That parameter and this parameter are really useful to us. This straight line, nobody's going to argue where that crosses the y-axis. And this turns out to be 1 over v max. No question what the value is. This, down here, turns out to be minus 1 over km. And again, no question what that value is. So Lineweaver-Burke gives us an unambiguous way of telling what we have to guess over here. Does that help? This is minus 1 over km, that's right, because it's in the negative territory over here. So if this came out as minus 1/2, you would take 1 over minus 1/2, you would get 2, that would be the km. Okay? Make sense? Yes? Okay. Any other questions on this? Okay.
So, one of the examples that you gave on the first problem for classroom problem,
Mm-hmm.
I don't know how to solve it in equation. You have 0.5 liters and then the axis of
Mm-hmm.
at maximum buffering capacity, 2 gas, 0.1 volts of HCl.
Okay, can I see the problem? Okay. So what was it? You have 0.5 liters of an acetic acid buffer, 0.8 molar at maximum buffering capacity. To this, you add 0.1 moles of salt. Is that the one or the other one? The first one. Okay, because they're different problems. How about if I do both of them? All right. Can I erase this? Okay. So I've got 0.5 liters of acetic acid buffer, 0.8 molar, and add 0.1 moles of HCl. And I say, what's the new pH? And the pKa, of course, for this acetate buffer is equal to 4.76. And so how do I do that? All right, here you go. Oh, here, I'm sorry. I forget who gave me what. Well, in order to work this, I need to have moles. And the reason why you might wonder, why do I do moles? Well, I can do moles because I can't add and subtract concentrations. I can add and subtract moles. I can't add and subtract concentrations. I can't add and subtract miles per hour 30 miles per hour plus 40 miles per hour equals 70 miles per hour. Well, what does that mean, right? But I can add and subtract miles to wonder how far I've gone, right? Okay. So I've got to be working in a unit that I can add and subtract, and the thing I can add and subtract is moles. Well, I've got moles already of this, right? Don't have to worry about HCl. How many moles of this do I have? Well, got 0.5 liters times 0.8, and now my molar becomes moles per liter. Doink, doink. And that's equal to 0.4 moles of buffer. There's one thing I want you to remember. It's when you see the word buffer, you think the following. Buffer equals salt plus acid. It takes salt and acid to make buffer. So if I've got 0.4 moles of buffer, I've got 0.4 moles of salt plus acid. Okay? If I add HCl to a buffer, what's going to happen? Well, let's first of all write our Henderson-Hasselbalch so that we're set pH equals 4.76 plus the log of, well, how many moles of these do I start with? Well, it said in the problem is at maximum buffering capacity. What does that tell me? Salt equals acid. Well, if salt equals acid and they add up to 0.4, I don't think it'll take you a calculator to figure out it's 0.2 each, right? Okay, so I've got 0.2, 0.2, but is that what I end up with? No. I add HCl. What happens when I add HCl? Okay, lose salt, add acid, and there's the solution to my problem. Okay? Now the second problem, I'd say 90% of the students get it wrong. Everybody looks at me for that. Okay? The second problem starts out exactly the same way. It's got this, but instead of adding this many moles of HCl, I add this many moles of salt. And the question is, what's the final pH? Okay? Now, I'll tell you how most people will do it the wrong way. So I won't embarrass anybody because they tell me and then they'll do it the wrong way. Okay? Most people do it the wrong way as follows. They say, oh, well, salt, okay, so acid made it go so that I got more acid and less salt. So if I add salt, this must be plus 0.1, and I lose acid, so I've got that, and that's my answer. And that's what 90% of the people will do. And they'll be wrong. Why are they wrong? Because they memorized a way to do something without thinking about what they were doing. Let's go back to our original equation. Our original equation said that HA goes to H plus A minus, right? And this equation said that if I take away H's with sodium hydroxide, what happens? This lets go of protons and makes more of this. So I lose acid, and I make salt if I add a strong base. If I put protons in here, what happens? Well, the opposite. This gobbles up the protons, so I lose salt, and I make acid. Now I'm adding salt. I'm not doing anything to the protons. I'm adding this. That's not going to take away anything. It's simply going to add more salt. So this is 0. I've added salt, but I haven't done anything to the acid. Okay? I see a lot of you nodding your heads. Good. Yeah? If I add a strong acid, if I were to add HA, let's say I added HAC instead of salt, that'd be a plus. Right? If you added HA, that's right. If you added a weak acid, that's what would happen. Make sense? Yeah. Okay. So what if so you understood what happened when I added this, right? What if instead if I added this? Nothing happens to the protons. I simply change the amount of weak acid, and the weak acid is down here. Right? So when I added the salt, you were happy with me adding this and saying 0.1 and this was 0, right? You weren't right. Okay, that's fine. Don't agree with me. What's that? Because when I add salt, I'm not changing protons. And so now, instead of adding salt, I'm adding weak acid, same thing. I'm not changing protons. Oh, yeah. Yeah. So there's nothing that gives me greater pleasure than teaching chemistry the way chemistry should have taught it. I really love doing that. Chemistry should have, it's not your fault. Chemistry should have taught you this stuff, and chemistry does a crummy job of this. I don't know why this is the case, but it happens all the time. Does that make sense? I'm a raving, ranting professor. That's what I am. So, yes? Have to consider what? Okay, so H2SO4 is an example of a strong acid. So what I care about is how many moles of protons I add, right? Doesn't matter if it came from an H8 or an H2 or an H4. If I told you I added 0.1 moles of protons, you don't care what it came from, right? But if I told you I was adding 0.1 moles of H2SO4, then you would have to take that into consideration, right? Because you'd have 2 protons for every one that you added. Right? Yeah. I like to keep things simple. There's enough complexity to biochemistry as there is. Clear as mud? Is this making you feel better or making you feel worse? Worse? Oh, God. I'm defeating my purpose here. What can I do to make you feel better besides showing you the key to the exam?
Are you going to do it?
I'm not going to show you the key to the exam. Huh? Well, I haven't even written the exam yet. I can make the key first and then. Well, see, all the answers are up here, right? Yes. Don't you hate it when professors tell you that? Yeah. Honesty is good here, right? So, I've told many of you, and I will repeat it here. I think that being in the right mental frame of mind, taking an exam is good. Okay, and I know it's a difficult subject, and I know it's something that's stressful, and I really don't want you to stress. I really don't. If there's something I can do to help you to feel better about it, I want you to feel better about it. One of the tips that I've given to students, and I've found a lot of students have found this works. If you have, first of all, if you have exam anxiety, they do offer sessions over in the Academic Success Center that will help you with that. But one of the things I found that's a very simple thing to do is the morning of an exam, okay, go out and exercise like crazy. And the reason that that works, we'll talk later in the course about stress hormone. So stress hormone is there in your body for a purpose, okay? The purpose of stress hormone isn't to give you a heart attack and it isn't to give you a stroke, but biologically it's there to help you escape danger, okay? So stress hormone is there. You're alive today because of stress hormone, because your ancestors escaped danger because they had the stress hormone and it got them out of danger. Well, stress hormone is aimed at getting you to burn off, run fast, get away from that grizzly bear that's chasing you. And it turns off your mind in the process because all the energy goes into your muscles. So if you take an exam and you're stressed, then it's like you're running away from the grizzly bear and your mind's not working, but your muscles are. Right? So the way that you get rid of stress hormone is actually with exercise. So that's why I say exercise, do a good exercise in the morning, and you'll be amazed at the difference that it'll make for you as you're burning that stuff off before you have to go and take the exam. Try it. Seriously. Okay? Here's where biochemistry can do you some good, right? Hopefully. Okay. I will be around my office tomorrow, so come and see me if I can be of help to you. Actually, I'll give you guys something I usually give my classes, and I forgot to give it to class today, but I'll write it down up here. You're welcome to call me on my cell phone anytime. And if that doesn't show up on the screen, I'll say it out loud for the TV people. 541-908-4465. Give me a call. Okay? I want you guys to do well on the exam. I really do. Study hard. Stay out of trouble. I want to see everybody out there jogging Friday morning. What's that? Yeah, sure. I'm not trying to get rid of everybody. Yeah, go ahead. Yeah. Well, let me tell you that I'll answer your question. But before I answer your question, put your fears at ease about something. Okay. So I don't give grades based on absolute percentages. I give grades based on patterns. So here's what happens. If I look at the number of students and I look at the score, okay, you've seen the bell-shaped curve, right? The bell-shaped curve is pretty accurate for what a class typically does. Okay? And so with a bell-shaped curve, you tend to have A's, B's, C's, D's, F's, right? Something like that. Where this occurs, which is the average, okay, is about where the C's hit, whatever that average is. So you can say you've got a low average, high average. The best thing that can happen to you is that the class has a horribly low average, and you're up here, right? Okay, so my favorite average on an exam is when the students in the class make about a 70. Because I feel that that means that the average student has gotten 2/3 to 3/4 of what I've taught them. Okay? That makes me feel good. I mean, I'd feel better if everybody got 100, I'll be honest with you. Okay? I truly would. Okay? But if everybody makes, on average about 70, I will be happy. Exam averages vary. Okay? There's one of the songs that I've written. It's about a class that I taught back more than 10 years ago. And this is a real world professor problem. It was my BB 450 class, and I gave an exam where I wrote a problem, and I inadvertently made this one problem almost impossible to solve, and I didn't realize I had done it. I thought I had written it a different way. And it was only after I put the key together that I realized, oh, shit, right? What have I done, right? Well, what happened was this about a 30-point problem, and about 3 people out of a class of 350 got it right. Well, what does this do to the average? Right? So the average on that exam was the worst average I ever had on any exam I ever gave, and that was a 47. So there's one, yeah, it's true. I wrote a song about it. It's a true story. I wrote a song about it at the end of that term. If you look at the song called Biochemistry Pie on my webpage, you'll hear the story about the class making 47. Well, it was a real-life story that they actually made 47. Well, I felt awful. I mean, believe me, there's no joy any professor gets in a low average or anything like that. And I said, whatever you guys need, whatever you want to do, we'll work. We're going to get this average up, et cetera, and we're going to do this. And, of course, a lot of it was the fact that this one problem was just a boneheaded problem, to be honest with you. And they turned it around, and that class, which had the lowest average ever, had the same number of A's, B's, C's, D's, and F's, okay, as any other class. Because if I had absolute scores, which is the way most of your professors grade, 90, 80, 70, 60, then a low average is really something to worry about, right? But it wasn't something for them to worry about, okay? And they realized that after that happened. So I tell you that so that you don't worry about what the average is. What really matters is how well you do relative to the average. That's really what matters, okay? Make sense? Does that help? I hope. Okay. Any other questions? Last call? Okay, guys.